Hello everyone. In today's video, we are going to discuss Prim's algorithm. The objective of Prim's algorithm is to find the minimum spanning tree. Before going to the concept of Prim's algorithm, note that Prim's algorithm is based on greedy technique. So initially we'll see what do you mean by greedy technique and how a problem needs to be solved in case of greedy technique. Note that greedy technique is one of the popular design methodology that we generally use in order to solve a given problem. And whenever we solve a problem, the solution to the problem can be categorized either as a feasible solution or it can be categorized as optimal solution. So if you note, I have mentioned that a solution to any problem can either be feasible or it can be optimal. What do you mean by feasible? A solution that satisfies a given constraint. If some constraints are being given to a problem and those constraints are being taken into consideration to solve that particular problem, then we call it as a feasible solution. Now coming to what do you mean by optimal solution? Optimal solution is a feasible solution for which the optimization function has the best possible value. So that is what we meant by optimal solution. Note that in case of solving a problem using greedy technique generally gives the optimal solution for a problem. This is the first point about the greedy technique. Now coming to how exactly we solve a problem using greedy technique. Generally in case of a greedy technique, the algorithm makes a choice that looks best at that particular moment. We generally call this as a greedy choice. That means whenever we solve a particular problem using any greedy algorithm, the algorithm makes a greedy choice. Now, whatever choice or choices we are going to make in each step should have the following requirement. So, these are the three basic requirements that should be there in the choice that we are going to make. The first requirement is it should be feasible. In the sense, the problem should satisfy the problem constraint. Now, as you see, that is a feasible solution is a solution that satisfies a given constraint, and optimal is nothing but a feasible solution. Hence, I can say that to get the optimal solution, it should have the property of feasibility. So, that is about the first requirement. Second requirement is the choice should be locally optimal. In the sense, it has to be the best choice among all the feasible solutions. And finally, the third important point is once the decision is taken, the decision cannot be changed or it cannot be revoked in the further subsequent steps of the algorithm. So note that this is one of the most important property of greedy technique. There is one more design methodology which is almost similar to that of greedy by name backtracking or branch and bound, wherein in case of backtracking or branch and bound, it also works on the same principles as greedy, but there we can backtrack. Once the decision we take, the decision can be revoked in the subsequent steps of the algorithm. But whereas in greedy technique, once the decision is being taken, it can't be revoked. So these are the three important requirements that we should keep in mind in case of solving a problem using greedy technique. Now with this, we'll come up with a general algorithm which gives us a rough idea about how a problem needs to be solved in case of greedy technique. This is a generic algorithm that we generally use in order to solve any problem using greedy approach. If you see, the algorithm is being named as greedy, and the description says that this is basically used to solve a problem using the greedy method. And the input to this particular algorithm is denoted with a list A of n element. That's mentioned here. A is the input, which is a list of n elements. Now, initially what we do, we assign null to the solution. Assume that the solution is a vector which finally contains my solution to the problem. Now there is a for loop being iterated from 1 to n minus 1, where n is the number of element. In any greedy algorithm, the number of iteration will be 1 less than the number of elements. So the for loop is being iterated from 1 to n minus 1. So there is a function by name choose which makes a choice. So x is equal to choose from A. Now I am going to check whether that X is feasible or not. If you have noted that in case of greedy technique, the greedy technique gives an optimal solution. Now what is an optimal solution? Optimal solution is a feasible solution. It should be a feasible solution first, which gives the best optimal answer. So if X is feasible, then what I do, I add this X to my solution, and this union is a function which adds the current solution to the previous solution. And finally I return my solution vector named solution. This is a most generic algorithm that we commonly used for all the algorithms which are based on the concept of greedy technique. Now in case of greedy technique, some of the most popular problems that we solve under greedy technique are, first one is the minimum spanning tree. And to construct minimum spanning tree, there are two algorithms. First algorithm by name Prim's that we are going to discuss today. The second one is by name Kruskal's. And the other algorithms that are more popular under greedy technique are, next is a shortest path algorithm by name Dijkstra's, and even the concept of Huffman coding, which is or Huffman tree, which is basically used to encode the data. Also, there is one more problem by name activity selection problem. Even to that particular problem also, we can go for greedy technique. Now we'll see what do you mean by a spanning tree and what do you mean by a minimum spanning tree, and then we'll go further to the Prim's algorithm. Coming to the definition of spanning tree. Note that a spanning tree of a connected graph is a connected acyclic subgraph. That means the spanning tree are nothing but a connected acyclic subgraph which contain all the vertices of the given graph. Assume that if this is my graph, which is a connected graph, so the spanning tree of this connected graph can either be this, or can either be any of these two. If you note, all these four are the spanning tree. The definition says that the spanning tree should contain all the vertices. It never says that it should contain all the edges. So first also in the first spanning tree also all four vertices are there. Similarly in the second one, third one, and the fourth one. This is the definition of the spanning tree. Now moving ahead, what do you mean by spanning tree? Let me define the minimum spanning tree. Definition of minimum spanning tree states that a minimum spanning tree is a spanning tree with the minimum weight. Now what do you mean by weight here? Where weight is defined as the sum of weights of all the edges that are used in the construction of the spanning tree. Now earlier for this given graph, I told these were the spanning trees. Now what I have done, I have associated some weight for each of those edges. Now this is one spanning tree. Now what is the cost of constructing this spanning tree? It is 20 plus 30 plus 5. It is 35. Now what about this? This is 20 plus 15, 35, 30 plus 5, 35 plus 5 as 40. Now coming to this, 10 plus 20, 30, 30 plus 15 is 45. Now coming to this, 5 plus 10, 15, 15 plus 15, 30. Now among these four spanning trees, which spanning tree took the lesser weight? It is the fourth one. So hence this fourth one is a minimum spanning tree. Now how to construct the minimum spanning tree? There are two methods. One is the Prim's and the second one is the Kruskal's algorithm. Now we'll see how Prim's algorithm works, and then we'll go for the pseudocode of the Prim's algorithm as well as its time complexity. Let me consider a graph with 6 vertices. Those 6 vertices are denoted with A, B, C, D, E and F. And ET is a set of edges which are used in the construction of minimum spanning tree. Hence, I have specified that the goal of Prim's algorithm is to construct MST. MST stands for minimum spanning tree, and the edges that are used in the construction of the minimum spanning tree should be finally there in this set ET. Now, initially this ET contains null. So, let me have this ET should contain all edges used in the construction of MST. Now, how many vertices are there? There are 6 vertices. Now, if you go back and see the generalized algorithm that we have defined, that we discussed earlier, stated that depending upon the number of element, the number of iterations should be 1 less than the number of elements. Here, the number of elements are nothing but the number of vertices. So here there are 6 vertices. So the number of iteration should be 5. So let me start. If this is first iteration, let me call this as the second iteration, this as the third iteration, this as my fourth iteration, and this as my fifth iteration. Now, coming to first iteration, I should start constructing the minimum spanning tree from one of the vertex. Now, I will take my vertex as A. From A, I will start constructing the minimum spanning tree. So, I will have VT as A. VT is nothing but the vertex that is being selected from where I start constructing the spanning tree. Next, what is there in V minus VT? If this was V and this is VT, so B, C, D, E, F. Now what I will do, I will see all the edges that is there from the vertex which is present in VT to I will consider all the edges which is there from the vertex present in VT to the vertex present in, to all the vertices present in V minus VT. Now, what are the edges that are going from A to B is there, A to E is there, A to F is there. I don't have any edge from A to C and A to D. So, the edges are A to B, A, E and A, F. These are the edges. Now, what is the cost of this edge AB? It is 3. Cost of edge AE is 5. And cost of edge AF is 6. Now, out of these 3, which is minimum? Minimum one is AB with a cost of 3. Now, what I will do? I will add this AB to my edge set ET. Now, my edge set ET contains AB. So, this is the first iteration. Now, going to the second iteration. So, my VT now will be having, I need to add the vertex that is being considered as a part of the edge added to ET. Now, onto ET I added B. Hence, my VT now contains AB and V minus VT now contains C, D, E and F. Now consider all the edges. From A to the remaining vertices in B minus VT, if so, as well as from B to this. So AC there is no edge, AD there is no edge, AE there is an edge, AF there is an edge. From B there is an edge to BE, there is an edge to BC. Now what is the cost of AE? AE cost is 5, AF cost is 6, BE cost is 4 and BC cost is 1. Now among this 4, which is minimum? Minimum one is this. So I should consider this edge. So my ET contains edges as first as AB and second one as BC. This is in my second iteration. Now in my third iteration, my VT contains the vertex AB which was already there. Now C is being added. So ABC and V minus VT as which are the remaining vertices D, E, F. Now now I need to consider all the edges from V to V minus VT. So I have AE first, AEF first as it is. Now from B there was an edge to E which was not considered, BE, this edge BE. So if you note in this two iteration, first edge considered was AB and second edge considered was which one? BC. Now AE, AF, BE and from C From C there is an edge to E and there is an edge to D. So it is CE and CD. Now what is the cost of AE? Cost of AE is CD. AE cost is 5. AF cost was 6. BE cost was 4. CE cost CE and CD. Please note that when you are taking the edges, first consider CD. First consider CD and then go for CE. Because while implementing, we generally use a for loop to iterate all the vertex. So first is CD and then CE. CD cost is 6 and CE cost is 4. Now which is the minimum here? So when you traverse this edges, first even I have an edge BE as well as I have CE. Now you should consider this. So this is BE. Now BE is the second next edge that I am going to consider. So my ET now contains, first it was AB, next it was BC and third it is BE. Now coming to fourth iteration, in fourth iteration my V will be ABC and E. Now my V minus VT will be D and F. Now consider the edges. So the first edge will be AF, A to F. With respect to B, nothing. With respect to C, it is CD. Now I can't consider this CE. I can consider this CD. Now if I consider this CE, there will be a cycle. So note that in the definition of minimum spanning tree, we have defined that minimum spanning tree is a connected acyclic graph. So we should not consider those edge which constructs a cycle. So with respect to C, I should consider CD. I am not supposed to consider CE. Next. Because E is already a part of E. Next, which is the other edge from C over E. From E there is an edge back to A, which results in a cycle. From E there is an edge to D and there is an edge to F. So E, D and E, F. Now I need to take a decision among these four which needs to be included. AF is 6. CD is, how much is CD? CD is 6. ED is 5 and EF is 2. Now among this 4, which is having minimum? It is EF. So I should go for EF. So my ET contains AB, BC, BE and EF. Now in the last iteration, in the fifth iteration, my V is ABC, D is not there, E and now F. So what will be there in B minus VT? Only left out is D. Now consider the edges. From A to D is there an edge? No. From B to D is there an edge? No. Is there an edge from C to D? Yes. C to D there is an edge. E to F, E to D there is an edge. Yes. Next, F to D there is an edge. Yes. Now what is the cost of CD? CD cost is 6, ED cost is 5 and FD cost is 3. So which is minimum? Minimum is this one, FD. So I should consider this edge. Now what my ET contains? So my ET now contains AB, BC, BE, EF and finally FD. So these are my edges which are a part of ET. Now what is the cost of this spanning tree? The edges that are considered are AD, 3 plus 1, 4, 4 plus 4, 3 plus 1, 4, 4 plus 4, 8, 8 plus 2, 10, 10 plus 3, 13. Cost of MST is 30. This is how Prim's algorithm works. Now we'll go for the pseudocode as well as the time complexity of the Prim's algorithm. Algorithm is quite easy to follow if you have understood the tracing of Prim's algorithm. Now coming to this algorithm is being named as Prim's, to which the input is a weighted connected graph represented with G. Now I have not written the description as well as the input. We know that the input is a connected graph. What is the output? Output is the set ET, which contains all the edges used in the construction of minimum spanning tree. Now coming to the algorithm, first initially I will put my start vertex or source vertex to VT. So VT contains V0. My V0 is the start of the source vertex. And initially ET will be null. ET will be null. Now this is the number of iteration. As you have observed, the number of iteration is nothing but the number of vertices minus 1. Hence, there is a for loop iterated from 1 to number of vertex minus 1. Now, what we do in each of the vertex, in each of the iteration, we find a minimum weight edge E star among all the edges. That means E star is nothing but V star minus U star among all the edges V comma U, such that V is a part of VT and U is a part of V minus VT. Now if we'll take that particular edge and then I'll put that edge onto ET and I'll put the vertex U star onto VT. Now VT contains VT, this is union, VT union U star, and ET contains ET union E star. And finally I am going to return ET. So this is about the Prim's algorithm used in the construction of minimum spanning tree. Now let's see the time complexity of the Prim's algorithm. Time complexity of Prim's algorithm depends upon how the input is represented. We know that the input to Prim's algorithm is a connected weighted graph. The graph can be represented either in the form of adjacency matrix or adjacency list. If the input graph G is represented in the form of the adjacency matrix, or I can call it as a weighted matrix, then the efficiency of the Prim's algorithm will be square of the number of vertices. So that is there mentioned in the first step. If the input graph G is represented as a weighted matrix, efficiency is theta of the number of nodes square. Now, if the input graph to the Prim's algorithm is represented in the form of the adjacency list, now what happens is the efficiency of the algorithm depends. If the input is represented in the form of the adjacency list, now what we do in case of Prim's algorithm, we know that it constructs a minimum spanning tree and the edges with the minimum weights should be considered. So what we do is we construct a priority queue. Priority queue is implemented as a min heap for on all the edges. Now how many times we perform the deletion operation from this min heap? It is nothing but the number of iteration. So note that the number of iteration is order of V minus 1. So this is order of V minus 1 is the number of deletion that we perform on the min heap to choose the smallest edge or to choose the smallest element. Now once we retrieve an edge from the min heap, now we need to reconstruct the heap once again. So, and it makes order of E verification and possibly changes the heap. We know earlier reconstruction of heap, it takes order of log V time. So the time complexity of Prim's algorithm, if it is represented in the form of the adjacency list, is the number of iteration here, plus order of E into log V. Logs. Now among these two, this is having a higher order, so it is order of E log V. So this is the efficiency of Prim's algorithm if it is represented in the form of adjacency list. Hope this is clear. Thank you.